And so for our second panel, we will be moving to the scale of objects and thinking about material properties, fabrication methods, and assemblage, and how that can unfold new design possibilities. So we will have one Mad Design Fellow from each of our three cohorts, and we'll hear from Lyle Regenvetter from Mechanical Engineering, Leanne Makatora from Electrical Engineering Computer Science, and GANIT GOLDSTEIN from Department of Architecture. So over to you, Lyle.
All right. Hello, everybody. Thanks for being here. The three of us actually have kind of discovered that we have a shared interest for computational design, so that's going to be a bit of a theme throughout the presentations and the discussion. I'm going to start off talking about generative AI in design, and then Leanne and GANIT will be talking about computational metamaterial design and textile design. So yeah, let's get started. Because Gen AI is so popular these days, I wanted to do a quick audience poll and ask people who has tried using some kind of Gen AI tool for a design-related task. All right, about half of the people. So I'm guessing a lot of you have had some kind of mixed feelings about it, right? So on the one hand, Gen AI tools are really excellent for conceptual design. This is a tool that's kind of borrowed from my lab mates. They're working on this, which basically goes from a design sketch and a text description and quickly generates a 3D model and a physical prototype. So Gen AI tools are really good for rapid conceptual design. I mean, this is able to go from a sketch to a physical prototype in minutes, which I think is really cool. So 2 thumbs up for Gen AI for conceptual design. It works really great. There's a lot of potential there. Now, the issue is that Gen AI tools don't do so well with detailed design or very specific design requirements. And to show this, I ran a little experiment here. So I asked GPT-4 to design a truss structure with 20 non-overlapping links. And this is what it comes up with. And I think if there are any structural engineers in the room, they know exactly what's going to happen here. But this truss falls down under its own weight. So, I mean, in a sense, it's kind of violated an implicit design requirement that we have, which is that, the truss should really support its own weight and probably a lot more. But if anybody's paying really close attention, they may have actually noticed that this truss violates one of our explicit design requirements as well, in that there are actually 21 links. There's not 20. So GPT-4, clearly fails to, satisfy both explicit and implicit design requirements. And this is a really big problem for detailed design. So I believe, I should also mention that, for all other types of Gen AI models in design, not just language models, we see the same behavior. So this issue with design requirements is really universal. So I believe that to actually get generative AI models to be valid or practical for detailed design, we have to think about ways to incorporate design requirements into the actual training process for Gen AI models. So you might ask, how are Gen AI models currently trained? Well, usually they just look at a bunch of examples, and then they generate things that look kind of like those examples, right? It's pretty simple. In design, this means that they're going to study, our favorite designs. We'll show them our favorite designs, and we basically say, do that, generate things that look like those designs, and it'll try its best to generate things that look like those designs. Now, the problem is that these Gen AI models are never exposed to examples of designs that violate constraints. So, most of us would have a hard time, following some rules if we never saw an example of somebody breaking that rule. It's kind of like learning from your mistakes, right? I think we all understand this intuitively. So I think the solution to this is that we need to show Gen AI models examples of designs that violate those constraints. And by training Gen AI models in this way, we can actually teach them to understand those constraints. This is something I've experimented with a lot. And we do see, in fact, that Gen AI models that see examples of constraint violating designs are much better able to satisfy design requirements, and in addition are a lot more data efficient. I wanted to highlight one more thing here, which is that thinking about design representation is also very important. This is kind of the lens by which Gen AI models see and understand designs, and by improving design representations, we can also improve the ability of Gen AI models to meet design requirements as well. I won't go into a ton of detail on that because I think Leanne will be talking a little bit about design representation, so I'll just use this as the cue to hand things over to her.
Great, thanks so much, Lyle. So my name is Leanne, and I'm a PhD student in computer science. And I work primarily on designing these small-scale geometric patterns that can actually induce interesting mechanical behaviors in 3D printed objects. And so what you're seeing here is a series of blocks that have been printed by the same 3D printer on the same run with the same material. But because of the patterns that we've chosen to fill each volume with, they respond in very different ways when you sort of poke them with a pen, in this case. I'm going to have the sample with me if anyone wants to play with it at some point. But these patterns that we've chosen to fill the volumes with are known as metamaterials. And you've already seen how these two examples can induce different deformation behaviors, but that's only the tip of the iceberg here. So we can also choose to design structures that are incredibly lightweight, but still preserve their strength. And if we consider different types of geometries, we can also come up with structures like these, which look a bit crazy, but they actually have the ability to block sound waves in certain frequency ranges. So you could use it for soundproofing or any number of other things. So even from these three properties, which again are really just scratching the surface, we can already see lots of applications for these sorts of structures in everything from aerospace to biomedical engineering. And so there's a huge push right now to understand the opportunities here, but that's incredibly difficult to do because there are so many different shapes we want to consider, and it's actually not clear which variations are going to lead to the properties that we care about. And moreover, it's actually not even clear how to characterize the design space we're trying to move around in because there are, again, so many shapes we want to be able to explore, and they're all characteristically different. So some of them have sort of these thin beams, some of them are these sort of sweeping shell structures, and it's hard to capture them in a unified way. And each structure itself is also incredibly complicated, so it seems like we're doomed to use some very high dimensional and inconvenient sort of representation in order to capture them all. And so a lot of my PhD has been working on wrangling this really unruly space and trying to impose some structure that lets us represent structures like the one on the top in a very compact way using the graph nodes that you see on the bottom. And just by simply recomposing these nodes, we can actually represent tons of different types of objects for the purpose of exploration. And once we have this representation, like Lyle mentioned, it becomes a lot easier to actually kind of traverse the space that we care about and look for interesting designs. And so in this example, we've embedded our representation within a human-in-the-loop interface, so you can build up and evaluate structures using the sort of integrated prediction tools. We can also imagine doing something more akin to what Lyle was showing with generative design tools, where you train on this representation and then allow a model to sort of give you suggestions that span the gamut of spaces. So here we didn't really impose a lot of constraints and we let it run wild. And as you can see, it came up with some pretty wonky structures that people might not have thought of. But because the representation is designed to be intuitive, it's also really easy to direct it in a certain region in order to get variations like these, which of course are still very diverse, but they share a common design thread as intended. And so there's, now that we can explore these shapes, it's much easier to understand not just how a single metamaterial will behave or impact its object, but kind of to start understanding the scope of possibilities and limitations here. One of the things that is most critical is really making sure that the things we are promising and predicting in our digital space are going to actually persist once we bring these objects into the real world. And that's something that I believe GANIT will be talking about more in her talk. And so I will hand it over to her. Thanks so much.
Thank you. It's been a pleasure to work with you and kind of think about the computational design world and how we are kind of really integrating lots of our work together. My name is GANIT GOLDSTEIN. I'm working on computational textile design, and I graduated from the Master of Science in Architecture from the Computational Design Group. I worked with Skylar Tibbetts in the Self-Assembly Lab. And it's a pleasure to kind of share with you many works that I've been working on for the last few years about textile design and kind of designing new relationship between past and future textile technologies. And I believe that textiles serve as a medium that connects stories between world perspectives and cultures. The projects that I will show today weave together past and future technologies for designing new relationship between the hand and the machine. And I'm looking at textile as a medium to combine those relationships with computational design, sustainable manufacturing, and embedding sensors into advanced textiles for extreme environment. Such as the example in the left that I will explain a bit, but it was a collaboration between many researchers across MIT to develop the new generation of spacesuit design using advanced fiber and sensing technologies. And in fact, the ways that we can produce very complex fabric constructions and garment is intertwined with the connection between coding and textiles. The Jacquard loom is a machine that wove complex patterns using punch cards for instructions, marking it as the early form of computers. Although the machinery for producing fabrics is very complex, the fabrics are still very much static. So my research investigates the potential for textiles. So investigates the potential for embedding new functions into textiles and accessories and garments. In my work, I'm interested in exploring embedding interactions such as self-forming fibers, growing natural colors into textiles, building interactive elements into the fabric, and connecting sound, color changing, and into the accessories of the design, and really designing interactive component in the physical and the digital format to build platforms that create new languages for design through interaction between garments and our environment. And these are a few examples of garments that connects weaving technique with 3D printing technology, combining all the new techniques for hybrid textiles. So up there, it's a documentation from my time in Japan that I learned ikat weaving, and then I combine it with 3D printing technology, but really kind of working on the layering process of how I can work with a 3D printer to produce those garments. This is an example of creating new fabrics using multi-material 3D printing. And it's very complex process because those pieces are assembled as there are around 24 panels that are all computationally designed without any sewing. So the idea is to really think about the labor-intensive process inside garment manufacturing and how we can eliminate that by computational workflows. So one of the things I've been developing through the time is designing for customization. So how do you make garments that are fit to measure to specific form of the body, and what does it mean to have garments that are fit to measure for a specific person? And those customization of garments are actually allowing opportunities to design new materials and new form that needed specific kind of properties inside the fabric themselves. So this is an example of a full garment that is produced from recycled filaments and recycled water bottle fabric. And here I tried to kind of think about the next cycle of the materials and how we can reproduce textiles from recycled material. And the last thing that I will mention is probably the present and the future of my work. This is a 3D knit spacesuit sleeve that I worked with multiple labs and collaborators across MIT, and we developed a sensing sleeves that can be kind of the future of way to produce customized garments for space application, and really embedding sensing technologies of fibers into the textile structure. So we use 3D knitting technology, 3D scanning, and fibers that can sense individual pressure on the skin, and really thinking about the future of sensing our body in advanced environment. Thank you so much.
Okay, so to kick off our little panel discussion, I thought I'd ask a question for all of us, really, because we're all interested in some form of computational design, which is ask, why bother with computational design? What are the benefits of using computing in design, and what do we really hope to get out of that broadly?
Yeah, I can start by just saying that it's actually a way to make crafts for me. So I always use 3D printing and modeling just to open a creative kind of workflow and experiment with different materials, and then kind of a way to go back to reality. So lots of my work is really reverse engineering kind of objects, produce them, testing them, and then, making the next generation of prototyping. So I think as a prototype kind of methodologies of trial and error, those kind of computational workflow are really important.
Yeah, I definitely resonate with this idea of prototyping. Computation allows us to look at so many more opportunities than we would be able to in sort of a traditional, find someone to fabricate it, test it, realize you were wrong, and then go back to the beginning. And this kind of reminds me of what Mariama and the first panel were talking about with this idea of not putting a Band-Aid on something after you've gone through the whole design process, but really trying to have the important things up front.
Yeah, I think to stress a very tangible benefit that all of us can hope to get out of computational tools is that, at the moment, the economics of design is that, most people design products to reach many, many different people. So this means that most of the designs that we have in our world are not really customized to our specific needs. And I think with computational design, we can hope to increase the throughput of design so that maybe one day we'll all be able to have customized products exactly built for our particular needs. So, maybe a bike that is fit exactly for my ergonomic needs, or for example, clothing that is exactly perfect for, your body type. I think one other thing that I'll quickly mention is this idea of design democratization, which is that ideally with computational tools or AI tools, we might be able to lower the barrier of entry to design. And I think, as designers, we often think about empathizing with the user, and there's nobody who can empathize better with the user than the user themselves. And if we can empower the user to use computational tools or AI tools to design their own products, then they're going to do a better job than anybody else could.
So one other thing that, because we're all computational designers, we're all obviously pushing this as a way forward, but something that's really important to keep in mind is when are we able to trust what a computational design tool spits out for us, and when is it important to kind of be skeptical or verify that information?
Yeah, I think that's a really important question, and especially for Gen AI models, which is what I'm working with, it's really difficult to trust what comes out of them. And I think the reason for that is because they are probabilistic models, which means that any possible output you can think of for a generative model, no matter how improbable it is, there is still a finite probability attached to that. So anything it could possibly come up with, there's a chance it'll do that. And if we're designing something in a safety critical application, we obviously don't want to roll the dice with small probabilities when people's lives are at stake. So it's very important to kind of verify what computational tools spit out in a lot of cases, especially with Gen AI models.
Yeah, I think I really connect to your kind of example of the spongy elements, because I think you kind of emphasize what's the properties that we need to each fabrication methodology. So if you use the same material and you can test it and fabricate it and really kind of compare, I think that's where things are much more moving from the digital to the physical and vice versa. So I think that's kind of a simulation tool. So it's not the aim to design through the computational workflow, but it's kind of the aim to fabricate those elements and see what's happening and kind of bring this information back to the computational workflow.
Yeah, I completely agree. So even though a lot of this resonates with me, because even though a lot of my design is not really based on these unpredictable AIs, it's very well established things like finite element method. There are still some things that we don't really fully understand how to simulate, like, what will the material properties actually be when you get it out of a 3D printer, and have we respected that? And so it's, even in sort of established things, it seems really important to to always double check and see what reality tells you is how you're doing. So I think at this point, I would like to throw it to the audience for questions. Is there any?
I guess we explained things really well.
Here we go.
Everyone's lost.
Hi, thank you. Lyle, I'm curious, when you have generative AI models that can successfully build some of these designs, what you see as the role of experienced architects filling in there and how they provide their expertise.
Yeah, I think that's a really good point. And I think we're very far away from the point where Gen AI models can do the entire design process. So I think a very tangible first step is this idea of human AI collaboration, where you have design tools that can automate certain tedious aspects of the design process. And then you have experienced designers who are familiar with the nature of their particular problems, who can verify what the AI does and leverage them to accelerate their workflow. So I see this idea of human AI collaboration as really the first step towards accelerating the design process for everyone. And I think that's a very tangible benefit to Gen AI that a lot of experienced designers and practitioners can hope to get out of it, if that makes sense.
Hi, my question is for Lian. I'm not sure if I'm pronouncing your name correctly. You're producing 3D printable materials with exceptional properties. So I was curious, do you define the properties before and then you explore what structures would support that? Or do you explore with structure and then decide what function could this serve?
Yeah, that's an excellent question. The answer is that it's useful to do both. And so I tend towards kind of examining the shape space first. So just designing the structures and seeing what comes out. Because I think that process of exploration is really fun and reveals things that we might not have thought to look for. And so that's my personal take. But it is also, I'm always designing things that can be used in a more targeted search, like you're alluding to. So where we say, this is what I'm designing, these are the requirements that it has, and this is what I would need my material to do, and then kind of work backwards in order to find the structure that provides those functionalities. They're both super interesting ways to go about it. There's a lot of work in both directions.
Well, we have time for one more question.
There's one at the top.
I have a question for GANIT. I'm curious if you have any hint on the next potential GPT for textile design. Let's say you want to have something specific. What are you worried about if that comes? And what are you excited about if that comes?
Yeah, it's actually a really good question. And I think the first thing that comes to my mind is actually designing new properties of materials. So it's almost connected to Lian works that you can, and my work in multi-material 3D printing. So you can actually design each pixel material properties inside the fabrication. So now it's much harder to control. It's much more in the fiber level of 3D printing. But if we can think about a voxel or kind of pixelizing material properties, we can think about how we are embedding new functions in each pixel of fabric. And that's, I think, the future of kind of this AI modeling, that you can fabricate lots of materials in one print, or kind of multiple functions that are constructed through the layer of the fabric. So one of the things I'm working on now is kind of thinking about fabrics that have multi-dimensional properties, so you can embed electronics inside each area and kind of fabricate where do you need what. And I think AI will be the perfect tool for that, for the future of multi-material kind of properties design.
Okay, thank you so much to our second panel.